Uh, Good evening. So I have principally only one topic left to cover, which is the Laplace equation in spherical polar coordinates, which I think we can finish up today. I posted a handout over the weekend related to solutions to the Laplace equation in cylindrical polar r theta coordinates. I want to briefly go over that and explain a couple of things today as well. I can also take questions related to your project if you have, because I had 2 or 3 questions today and they are all similar. So I can answer some of the questions related to what you are up to, general clarifications, because odds are your question will be also shared by somebody else in the class. So feel free to ask something if you have. Yeah. Yeah. So yeah, that's something that came up today. So if you have a domain, and let's say this is x equal to a and x equal to b, if you have an equation of the form whose general solution is y of x equal to c1 j nu of x plus c2, let's say y nu of x. This is your general solution. The whole point of this project is to force you to deal with this Bessel function of the second kind, which if the starting point a is 0, the only way you can get this to be a solution is to choose c2 equal to 0. So I am forbidding that. I am asking you to choose a to be non-zero so that your domain is a less than x less than b, and you have to specify y at x equal to a, or the slope of y at x equal to a, or you can specify y at x equal to b or the slope at x equal to b. You can have a combination of these two as your boundary conditions so that you would be forced to deal with C1 and C2 both being non-zero, and you'll have to use the y nu of x. So you can choose your boundary conditions, just don't include 0 in your domain. It Well, if you use this to represent a temperature profile or a voltage profile, what you could what I mean by analysis is the solution to this y of x is in the form of these Bessel functions, which themselves are infinite series. You know that j nu of x is essentially an infinite series from n equals 0 to infinity. So each value of n is a potential solution. Like for example, you can take this first term for n equal to 0 or 1. That alone is a potential solution to your original ODE. So if you are thinking of a solution which is multimodal, you can think of an analysis. How does the first mode look like? How does the second mode look like? What part of the solution amplitude is contained in the first mode, second mode? In fact, if you even though this is an infinite series, mode after the third or fourth mode, the terms are practically zero. So they may not contribute much to the solution. So you could try to see how much of your amplitude is contained in the first few terms than the next infinite terms. That sort of simple analysis is what I'm asking you to try. Something. Okay. I saw a couple of codes also today. If you have a for loop in which you construct or you run the loop for a few number of times to compute each term of this infinite series, at least for this project, it is sufficient. In theory, when you are using Bessel functions in your research, you would just call the Bessel subroutine in MATLAB and it will give you a very precise estimate, which is how you operate in reality. But forcing you to write a for loop or a while loop to get this is to make you deal with the terms to get you that familiarity. Okay, so I want to see basically one for loop to compute this and this. You can even put them in the same loop because you're going to they have similar terms except it functionally is a little different. Okay. So don't include zero. That's my message. The starting point of your domain is not zero, should not be zero. All right. I want to quickly go over the handout that I posted because it's been nagging me that we haven't seen that polar coordinates. So this is your Laplace equation. One second, let me make sure I started recording. Yep. So this is your Laplace equation in polar coordinates with only r and theta. And I'm sure all of you know how that coordinate system is defined. There is a center, and any point is denoted by two coordinates, a radius and an angle from the reference angle, like theta equal to 0. This by itself does not tell you what your domain is. A domain is defined by a physical surface on which you apply a boundary condition, and it divides the region between your computational domain and the external universe or world. In the sense, let's say you are trying to use this equation to model the voltage or the electric potential around a circle. There are two domains you can define. One is the circle, which is the boundary surface. The area defined by r greater than the radius, or the area defined by the interior of the circle, r less than radius. So both equations are modeled by the same, both situations are modeled by the same equation. There is a very subtle difference of how you would use that information while you are selecting or constructing your general solution. Okay. So steps are very similar to what we have done so far. Use separation of variables, write that in terms of two functions, separate the variables and call this say minus k, okay, and you can write down the two ODEs in this form. Okay, so the reason we write this minus k is purely to get something that is going to look like our Bessel's equation. I'm sorry, our Euler-Cauchy equation. If that is plus k, this has to be minus k. And last time, the question was or came up, how do we select values for this k? Like, should we just, is there a magic rule or something to this? Okay. So when I set up this equation using Frobenius method, I start with a general idea that let the solution be of the form r power nu, where nu is to be determined, multiplied by infinite series am r power m, which is the solution to that ODE. And I have this B naught and C naught, using which, what is the next step? Whenever you do Frobenius method, the next step is to write the indicial equation. The reason it is called an indicial equation is that it is to solve for this index nu, which multiplies with the general power series. So you write that, you arrive at this equation. Nu squared plus k equal to 0. Until now, we have made no presumption about what is k. Here we choose minus n squared, which I did. I didn't try to copy this from any book or something. I just thought about what is the only way this equation can lead to any meaningful solution for this ODE. That's the only thing I can think of. And if I make this particular choice, it gets me one, solutions that look mathematically simple. Number two, those solutions connect with my intuition about how the world works. In the sense, if I choose k equals minus k squared, I'm going to get plus or minus n, from which I'm going to choose either plus n or minus n. I'll come to that. But if I choose plus n or minus n, I end up with something that is either r power n or r power minus n. I told you my problem is something like a circle on which I apply a voltage, and I want to calculate the electrostatic potential either outside or inside that circle. I know somewhere in my head that electrostatic potentials have to decay with space, and they have to decay over 1 over r or r squared or r cubed, because there are charges, there are dipoles, there are quadrupoles. Like there has to be a certain method to this pattern. So I know this physically makes sense. And compounding these two facts, that is one, this seems to be the only way to get a solution. And two, it leads to me to something intuitive that I can relate with, is a justification that I can come up with to choose k equal to minus n squared. Of course, if you are an applied mathematician, you might be able to look at this, this original equation, and you might be able to discuss a broad range of possibilities for k in order to end up with different types of ODEs and solutions. But we are not that, or at least I'm not that. So I end up with, or I settle with what is intuitive to me, which is to choose as minus k squared, okay, or minus n squared. If I do that, I get two choices. I can do plus n or minus n. This was written later. That is, if I'm doing this like you as an example problem, I get plus minus n. Only thing I know right away is what? Just without this, what can you say from plus minus n, where n is a non-negative integer? This is Frobenius method. You solve your indicial equation, you're going to get two roots. What do you do when you have two distinct roots? Two distinct roots that don't differ by an integer. If nu1 and nu2 are distinct, h1 is r power nu1, h2 is r power nu2. So you get two linearly independent solutions. All you have to do is figure out what the coefficients are. We did this earlier in the semester, like before the first exam. If n happens to be a repeating root, like same value, you would take this h1 to be r power n or r power nu, and the second solution you would construct using a logarithm. Same thing you would do if nu1 and nu2 differ by an integer, which is the case here. So whatever n is, 2n is an integer here, right? So first solution is really simple. Just pick n equal nu equal to n, and then what we do is to go through the solution process, substitute for h using the infinite series, solve for am, and you would find out that am is actually 0 regardless of what m is. That is, for m equal to 0, a0 has to be non-zero, and for any other m, am is just 0, which means your solution is r power n. Look at this expression. When will this be finite valued, and when will this be running towards infinity for r? Like what values of r will make it go towards infinity, will make it blow up? So if your r is boundlessly increasing, this function will keep boundlessly increasing. So this is a solution which cannot be physical if you are thinking about the external domain. For r greater than the radius of the circle, this won't work. It can only work if it is within the circle or r remains finite value. That's why later I wrote plus n works if radius is bounded by the circle and other way. Okay. Okay, so you have one solution h1, which is r power n. Now, how do you get h2? You can follow the table in the book, but this method is something that you don't have to rely on your memory. This will, if you learn this, it's a really simple technique, which is to just assume h2 is some nonlinear function multiplied by h1, and then repeat the process. Now, if you substitute h2 back in the original equation, you get the derivatives. You substitute this back. At some point in your derivation, you will get to use the first equation, which is a solution to the original equation, and end up with the equation for u prime in terms of r. So you can integrate this to get u of r is equal to r power minus n by 2. Remember what was h1? h1 was r power n. h2 happens to be r power n minus 2. Okay. Sorry, h2 happens to be r power n minus 2 multiplied by r power n, which is r power n over 2. This is your complete function. And r is bounded. That is, r less than or equal to uppercase r. The problem with this solution is what happens at the center of the circle. You tell me what is the physics or what is the mathematical constraint at the center of the circle at r equal to 0. Well, as written, if you just consider h of 0, h of 0 is just 0. That's not a problem. The problem is not h of 0. The problem is the derivative or the slope of the function at 0. Here's a mathematical statement. H dash of 0 must be 0. Physically, you tell me why that must be true or what does it mean to be 0. When I say constant, that I could just say h equals constant. Why am I saying the derivative with respect to r at the center is 0? What does it physically mean to say that?
Is of a disk. If you said an example, like if you are putting some external electromagnetic forces on a disk, then either at the center it will be minimum or maximum.
Well, it is the maximum or minimum. That is what you're translating what h dash of 0 is 0 means. I'm asking why would it be 0? Why should it be 0? That's any angle. That is, your solution depends on r and theta, right? You can approach it along the line theta equal to 0 or theta equals 90 or 45. In any angle you approach, that point has to have the same value. That you can ensure by saying that partial derivative of h with respect to r is 0 regardless of which theta you come in. That is what we enforce by saying h dash of 0 equal to 0, which should imply, okay, which means this equation here, if you take its derivative, this is n power n over 2, and this is n over 2. This is 1 over square, n by 2 minus 1. N by 2 minus 1. Okay. It will be fine everywhere, even for other values of n other than 0, but for n equal to 0, this will be r power minus half, which is now a problem because r power minus half at r equal to 0 will blow up. So we have to avoid that possibility by setting C2 equal to 0. So that is how you use the information at the center to set C2 equal to 0. So then your function, I'm still talking. Can you wait? So that your function happens to be C1 r power n, so which is r power n with C2 equal to 0. Yes.
The shape of our answer with like that.
If that would be continuous but not differentiable, your function has to be analytic. So that's why we choose this. Okay. So we have h of r. Now that you know that k takes these values minus n squared, you can then solve for q, which will get you trigonometric functions, which you can write out as the complete solution for u as the product of h and q from n equals 0 to infinity. And you can write it in this form, in the form of regular Fourier series. And then the boundary condition specified on the circle, which is like a function of only theta because it's on the circle. This can be used to evaluate the constants. Okay. So you can evaluate the constants, and the same problem repeats if you are interested in the external domain. Just make the other choice. Everything else remains the same using the boundary condition. The only constraint is your function h has to be finite valued when r goes to infinity. That you can ensure by choosing the other function r power minus n by 2 to be 0, and this is the remaining part. So we get this complete solution. Again, I think I mentioned last time, if you look at problem set 12.10, all the way from problem 4 to 18 is essentially problems of this type. This is the general solution. You would apply the given boundary condition in the exam to get the Fourier coefficients. Okay, so places where this can, variations of this can be given. If I give this f of theta just to be a constant, that will make your life simpler. Otherwise, this integration will be a little bit involved, but again, not too complicated. Something we can easily do. Okay. So this I posted. Kindly take a look. The book doesn't really make a distinction about this internal and external domains, but I think it's still useful to keep that in mind because at least in engineering, mostly you're interested in the, I mean, you could be interested in both. I wouldn't say only one. All right. So the last topic in our PDE discussion is the Laplacian in spherical polar coordinates. Which is section 12.11. And we want to solve. So first of all, spherical polar isn't actually as simple as the others. So if you have any given point P, it is represented with three coordinates, r, theta, and phi, where r is the distance from the origin. Theta is usually denoted as the polar angle. And phi is the angle in the horizontal plane below, referred to as the azimuthal angle. The complete equation would be URR plus 1 over R UR, sorry, 2 over R UR plus 1 over R squared u into plus cotangent of phi plus 1 over r squared sine squared phi times u theta theta. Again, looks very lengthy. We'll see somewhat how these equations come about when we do vector calculus. But for our problem solving exercise, we are trying to look at a simpler version of this problem, which involves only the r and phi coordinates. We assume that any dependence on the polar angle is 0. Okay, which means we are interested in obtaining solutions that depend on r and phi. Okay, so that would be 1 over r squared to 0. So this is our equation with the boundary condition u of r comma phi is some function of p, and the limit r tends to infinity of u of r is finite value or generally 0. I'll give you 5 to 10 minutes time. Can you end up with the two ODEs from this PDE? Start with the separation of variables. Write u of r comma phi equals h of r times q of phi. And let's get two equations, one for h and the other for q. Can you do that, please? Be consistent with the book. They are using g of r and h of phi. G of r and h of phi. ODE for g and ODE for h. By stating this, we have kind of already said r greater than or equal to uppercase R. Are you getting this? Right? I mean, just substituting and collecting the terms into each equation. So what is this equation? This is going to be dash plus infinity h double dash plus kh sin phi equal to 0. We will start with this equation. So usually here at this point, our strategy has been what? Trying to tie this back to one of the template equations we have seen before and thinking along the lines, what choice of k will get me something that resembles a Legendre equation or a Bessel's equation or an Euler-Cauchy. Last time we chose k equals minus n squared. So here, of course, the book says to do something differently, but what I want to see is how can we guide our intuition towards that. You can make two choices. One we have already made k equal to minus n squared. The other choice the book suggests is k equals minus n into n plus 1. Okay, where n is a non-negative integer like 0, 1, 2, and so on. You can make either choice, of course, but what intuition do you gain from making the second choice versus the first choice? Or let's just talk about the second choice for a second. How can we connect this with some physics? So if you make the second choice, you get g double prime plus 2 over r g prime plus n times n plus 1 times g equal to 0. Okay, that is k equals minus n times n plus 1. What is this is again something that looks like the Euler-Cauchy equation. And if you take the initial equation, let's assume g of r is of the form r power nu summation m equals 0 to infinity am r power m. You would write the initial equation, which is nu times nu minus 1 plus b naught nu plus c naught equal to 0. What is b naught? 2. What is c naught? N times n plus 1. So you have nu minus 1 plus 2 nu plus n times n plus 1 equal to 0, or nu squared plus nu plus n times n plus 1 equal to 0. Is that correct? How do we factorize this? Nu times nu plus 1 plus n times n plus 1 equal to 0. How do you solve for nu here? Well, you can of course take this and apply the quadratic formula. Right? What is nu? Minus 1 plus minus square root of 1 minus 4n divided by 2. They're taking us anywhere. No. What do we do? The first thing that actually the book suggests is not to include the negative sign. That is a mistake on my part. We just say n times n plus 1 to get negative of this. C naught will be negative, negative, negative. So this will be positive. Okay. Sorry. No imaginary roots. That is, if n is positive integer, this will still be a positive number. But let's just think what values of n will actually simplify this. A times a minus 1. Yeah, plus 2a. Okay, so a squared plus a. What we have here, mu squared plus mu. So in not this way, we want to write this mu squared minus n squared plus nu minus n equal to 0. So this is nu minus n times nu plus n plus 1 equal to 0, which will make nu equal to n or minus of n plus 1. So you get two solutions. Now based on the understanding that r is a positive, r is a number greater than the radius, which one should be rejected? N is a non-negative integer, which means we have to reject mu equal to n. So our solution g of r would be r power minus n minus 1. If you contrast that choice with the other choice of, let's say, k equal to n squared, I want us to see what is the difference between spherical polar and cylindrical polar. So if you take k equal to n squared just for the heck of it, and we put it here, g double prime plus 2 over r g prime minus n squared g equal to 0. So this is nu times nu minus 1 plus 2 nu minus n squared equal to 0, or nu squared plus nu minus n squared equal to 0. Nu equals minus 1 plus minus square root of 1 plus 4n squared divided by 2. What will this get us? Non-integer values for nu. What's the problem with non-integer values? It's not a flip question, like I'm not asking you knowing the answer. I really don't know. One of the things I want you to think about is why this particular choice. It's not told in the book. Okay, why this particular choice? We know that if this particular choice is made, we are going to get this solution. But why? Why this choice? Think about it. We'll talk about it next lecture. Okay, I don't know. I'm not like, I also have to go back and think about this. Why this choice? Because this whole art form now comes to being asking or selecting values of k that eventually determines the type of solution you are going to get. You made a change here. If you had done this without thinking too much about it, you will get values of mu, and you would write equations of the form that looks like this and keep proceeding. But since we have a book and they tell you exactly to do this, we end up with this and reject n and take n minus n minus 1. Why? Okay, that's a question to think about. So we are moving forward with this solution. Ag of r, I'll write it Gn of r. And so I have my other equations for h, which is, I forget where I should it. Yeah, this one. In this one, I'm going to write k equal to minus, sorry, k equal to minus n times, sorry, plus n times n plus 1, k equal to n times n plus 1. Okay. How do we solve this equation, which is in terms of phi? So this is cos phi times dh over dphi plus sin phi times d squared h over dp squared, which I should have written first. Sin phi times second derivative plus cos phi times first derivative plus n times n plus 1 sin phi times h. We'll do a simple transformation. Cos phi equal to w, which implies dw by d phi is minus sin phi, okay. And if you want to use, you want to get dh over d phi, this is dh over dw times dw over d phi, which is minus sin phi times dh over dw. And what is second derivative? First d over d phi, d over dw of dh over d phi multiplied by dw over d phi. I'm getting the first and second derivative to plug it back in this equation. Okay. So what is this? This is d over dw, dh over dw times dw over d phi multiplied by dw over. Can I write it that way? This is d over dw, dh over dw times minus sin phi multiplied by minus sin phi. So this is sin squared phi d squared h over dw squared. And since cos phi is equal to w, I'll write this 1 minus w squared d squared h over dw squared. The whole point is to write this ODE in terms of W, instead of phi. So let's see here. I have sine phi, and then I have d squared h over d phi squared. So I would have, sorry. Yeah.
So like in the second line, you know, there will be two terms.
This one.
Yes,
So I took the derivative, I mean, okay,
so the third line, like,
here
yeah, should be two terms.
sine phi, I mean, where should you think you should be, there should be two terms? Or you mean say you are saying we should differentiate this?
Yes, like, we,
Right, so let's think about this. So this is minus sine phi multiplied by minus sine phi times d squared h over dw squared. And then you're saying we should differentiate this, which if we do, this would be minus dh over dw times, what is the derivative of sine phi with respect to w? That would be cos phi multiplied by d phi over dw. What is d phi over dw? Yeah, minus 1 by sine phi. So this is minus 1 by sine phi. Doing this right? Okay, so now we would have minus sine phi second derivative, and then I would have plus sine phi, no, sorry,
Part phi.
yeah, plus cos phi times sine phi, or divided by sine phi times dh over dw, which would be sine squared phi d squared h over dw squared minus cos phi dh over dw. Okay. All right, so let's try to regroup here. So d squared h over d phi squared equal to, what is sine squared phi? It is 1 minus w squared d squared h over dw squared. And what is cos phi? Is minus z times or minus w times dh over dw. Okay. And dh over d phi is minus sine phi times dh over dw. So I'm going to take this equation and I'm going to divide throughout by sine phi. Let's see what happens. I get d squared h over d phi squared plus cos phi divided by sine phi dh over d phi p plus n times n plus 1 times h equal to 0. So this will be here, this will go here, this is just h. So I'll have 1 minus w squared d squared h over dw squared plus cos phi over sine phi times minus sine phi times dh over dw plus n times n plus 1 times h equal to 0. So this is 1 minus w squared h double prime minus w h prime plus n times n plus 1 times h equal to 0. That was a good save. I think this one, I missed the beat, but you got it. So just making sure that this is of the same form that the book writes it. What they have here is d over dw 1 minus w squared times h prime plus n times n plus 1 times h equal to 0. This is what they have. Let's make sure we also got that. This will be 1 minus w squared times h double prime minus 2w times h prime. You're missing a 2. We are missing a 2. Forgot about this, didn't we? No, we have it here. Okay. Oh, I did forget about this. I didn't write it here. So I did forget about this. One minus w squared times d squared h over dw squared minus w times dh over dw. So now this comes to minus 2, which checks with this. So after all this, we have 1 minus w squared times h double prime minus 2w prime plus n times n plus 1 times h equal to 0. What standard equation does this fit into? Since we are doing spherical polar, you can preempt and say it's Legendre's equation, but let's go back and write down the Legendre's equation and make sure we got it right. Okay. So Legendre's equation from chapter 5 is 1 minus x squared times y double prime minus 2xy prime plus n times n plus 1 times y equal to 0. That is Legendre's equation. And for integer values of n, you get the so-called Legendre's polynomial. This is Legendre's equation for non-negative integers n equals 0, 1, 2, and so on. The solution to this equation is y of x equal to Pn of x, where Pn of x is the Legendre's polynomial of order n. And for sake of completeness, I'll also write the polynomial. N of x equal to equation m equal to 0 to m. This one for m 2m minus 2m factorial divided by where m is equal to n by 2 or n minus 1 by 2, whichever is an integer. These are all things we discussed back in module 2 of chapter 5. So our equation here is the Legendre's equation of order n. So we can write h of w is equal to Pn of w. Since it depends on the integer n, I'll write Hn of w. Already we also wrote Gn of r is r power minus n minus 1. So we can write that combined function u of r comma p, which is like writing u of r comma w first of all, is n equals 0 to infinity Gn of r times Pn of w multiplied by an arbitrary constant An, which we can write summation n equal to 0 to infinity An divided by r power n plus 1 times Pn of cos theta. I'm sorry, cos phi. The first boundary condition, which is to say u of r comma phi in the limit of r going to infinity, obviously this function will satisfy that because this term will guarantee it. Because we intentionally chose this value of the new parameter to ensure this function remains finite valued for large values of r. If this were the other way, that is, if we are interested in a sphere and we are interested in r equal to 0 to r, say we say that internal domain, in that case we would reject mu equal to minus n minus 1 and choose r power n or choose n, which will give Gn of r equal to r power n. What is the very last step? You have used one piece of boundary condition at infinity what is the other boundary condition which we still haven't used? It's the value of the function u at the surface of the sphere. Right? We also were told u of r comma phi equal to some function of p, which could be a constant or something that changes with angle. You can think of phi like an equatorial angle. It's the angle that is formed in the equatorial circle or equatorial plane. So to complete the process, we would say u of r comma phi, which is only a function of phi, is equal to summation n equal to 0 to infinity an over r power n. I would have Pn of cos phi, Pn of cos phi multiplied by, yeah, Gn is already fixed. Ans are Fourier Legendre coefficients, just like we did Fourier Bessel and Fourier series. So An would be, in our case, R runs from R to infinity. The domain extends from the surface of the sphere to infinity. We would have, oh wait, sorry. We are looking at the angle here, 0 to 2 pi Pn cos phi d phi. Okay, Pn cos phi d phi divided by r power n divided by 0 to 2 pi f of phi d phi Pn cos phi squared d phi. And I believe since this is integration with respect to phi, there is also going to be a sine phi involved. Just making sure. Yep. Why am I multiplying by sine phi? When we did the Bessel series, we multiplied by r dr because we represented the area. In this case, the area element will have r squared sine phi d phi d theta. Theta doesn't matter because of both in numerator and denominator it will cancel out. So you are left with r squared, which will also cancel out. So you are left with only sine phi d phi. So what I've also figured is that if I'm going to give you such a problem in the exam, either using Legendre's polynomial or Bessel functions, to simplify this squared term, the norm term on the denominator, I'll try to give you identities which will allow you to transform this into a higher order function and do the integration somewhat simply instead of having to go through the square. Okay, so I'll try to simplify it as much as possible, but the kind of skills I'm looking for is splitting the equation into two portions, selecting the correct solution, which is physics driven, applying the boundary conditions, and eventually at least coming up to this integral. After this, the evaluation will maybe only 10 to 15% of the credit. But if you get here correctly, following all the steps and correct decisions with assumptions, stating them, you should get at least 85% of the credit. Split the equation, separation of variables, number 1 here. Choosing the correct solution based on physical reasoning, saying I am choosing this and rejecting this for such and such reason. Step 3 is coming up to here to write the integrals for the coefficient. Step 4 is computing the coefficient. So if you do 1, 2, 3 correctly without having enough computational speed, you should still get 85% of the credit. That is the idea. Yeah.
So from the start of this question, we expected to do that entire thing in 20 minutes.
Not exactly 20 minutes. It's 3 problems, 80 minutes. So over 20 minutes. But you don't have to go through all the steps that I did today. If it's an equation that starts with either the term spherical polar or it has, you can look at the equation. You can directly jump ahead to this and the other equation for theta. Okay. I don't expect you to do all the steps.
Okay.
You are allowed to bring notes. I would suggest at least for this and the cylindrical form, try to have the derivation kind of something you can refer and skip to the last step of the derivation. I don't need to see the intermediate steps.
Sure.
The only reason I'm not allowing a open book exam is because some students said they don't have the book. But even now, if all of you are saying that you have access to the copy of the book for during the exam in a paper form, I'm ready to do an open book exam. This exam is not about remembering stuff. It's about applying stuff. So I'm okay if you bring your book. I have one copy which I can loan. Can you find friends who can loan you the book for 2 hours and like 80 minutes? Think about it. We'll talk on Wednesday. Okay. Again, yeah.
Oh, there, right, there's a sign, theta, like the,
This one.
yes.
So we think of a sphere. And the surface of the sphere is defined by r equal to r. Because this expression is evaluated on the surface of the sphere. Okay. And what we want to do is to get a patch of the area and integrate this. This patch is on the sphere and you want to cover the entire area. So what is the area element? That would be r sine theta d phi and r d theta. Actually, I should write it the other way. This is r sine theta d phi and this is r d theta. So the area element is dA is r squared sine theta. Wait. Yeah, sorry. So if you take an element and angle d theta, the area swept or length swept is r d theta. And then if you have to take another length, that would be the projection of this, okay, which would be r. This would be cos theta. So this is sine theta, r sine theta d phi. So the area element will be r sine theta d phi. So this will be r squared sine theta d theta d phi. But what we have is sine phi. I wonder why. Thought this was. Oh. Forget what I said about the area. So if we go back here, this one here, you have already transformed your coordinates from phi to w. So you have w, what is the transformation? Cos phi equal to w. And cos phi varies between -1 to +1. So your w varies between -1 to +1. Okay. So you can write this integral in terms of w where W is a linear dimension. It's not an angle, it's a length. You have projected an angle into a length. So you can get AN first in terms of dW. And then if you make this substitution for W, you will get dW is what? dW is minus sine phi d phi. That is how we end up with this sine phi. I was mistaken to think it was an area thing, but it's not actually the area. It's just a transformation back to the original variable phi. Thank you for the question. Okay. So next lecture, we don't really have any topic to cover. What I would request you to do is bring suggestions or requests for different problems. We'll try to set up at least 3 or 4 problems to sort of like I can simulate the exam. Like I want to give 3 problems for the exam. We'll try to do 1 of each type. Okay. Yes.
Will that replace the mock exam, this review?
Yes, this review, basically I have 1 lecture just to do review. Instead of posting a mock, I will actually bring the mock and put it in the board and we can discuss the solution to the mock. Okay.
Will it be the same difficulty as the exam?
Yes, this is what last time I got the suggestion from Jeffrey that make the mock tougher than the exam, which is what I will try to do. So I'll try to over prepare you in a sense. Hopefully that you will all be successful in the. See, in the exam, it's really about, it's not hard work. It's going to be smart work. Have your lookup sheet in front of you. You should know which equation to pick and its solution to write. C1 times the first function plus C2 times the second function. You should get to that in like 5 minutes. After that, it's about applying the boundary condition and solving for C1, C2. I don't want you to do any derivation in the exam. Should be able to reduce all of this into a lookup table, and that you can only do if you do enough problems that you know where the bodies are buried. Okay, so practice more. Thank you.